Hi guys, it's been a while since my last video, but I think in the last one I had built this serial output circuit, and I did this with the intention of hooking it up to a 6502 computer. The idea was building it from individual parts like this. I could make something that didn't require any configuration in software, which would allow the 6502 computer to very easily output data for debugging purposes, help diagnose stability issues and things like that, without depending on it having a decent kind of software initialization of an ACIA or something like that. So this is substantially the same circuit I showed in the last video, I think. Most of this stuff was already there. There are a couple of things I've added in though. This chip here was an 8-bit register, and it's feeding its data into a shift register, which is essentially what makes it get sent out over the wire, which I believe is the orange line here. Over here we have a flip-flop that's used to coordinate the start of the process, and then this chip here is a 40103 down counter, which is used to divide the input clock, which I think comes in on the red wire here, by a certain amount in order to generate a Baud clock, which is a sort of bit speed clock. There was actually a mistake in the configuration of this, which David Banks has pointed out. I configured it to be one less than it should have been, and that meant that it wasn't actually outputting the right baud rate. But in any case, the actual divider is going to need to change because I'm not going to connect it to the same clock that I was using previously. So we'll have to come back to that later. In terms of additions, I've added another 40103 down counter over here, and this one's configured to divide by 9, and that's in order to count the bits that this one is generating, so that once we've sent 9 bits we get a signal which goes back to the flip-flop, and that signal at the flip-flop is then used to be able to tell the computer that the byte has been transmitted, so that the computer knows it can send another one. And in order to get that back to the computer, we need to tri-state that output. So this green wire here is taking the result of that kind of test and feeding it through this bus transceiver. It's a 4-bit bus transceiver, which is connected to the top 4 bits of the data bus. And I think it's the top one I've wired through to that signal. So when the CPU reads from this transceiver, it can test the top bit and determine whether it's okay to send another byte yet or not. This transceiver is going to be activated by this signal here, which we'll need to connect to the computer as well, and I've also connected these yellow wires to the inputs of the 8-bit register, and these need to go to the CPU's data bus. Now I'm not actually going to hook it up to the same computer that I was using last time, because I was a bit tired of that one. It was having stability problems and I didn't like it very much. I built it around the design that Benita was using, with the hope of making it a little bit more accessible for you guys, but the design of that computer is a little bit limited and I wanted to do something different. So what I've built to use instead is this one. Now the purpose of this computer was basically to run at the fastest clock speed I could. It's not something I've really cared about very much in the past. I've been much more interested in the sort of peripherals that bolt onto the computer, but there were some really interesting forum posts on the 6502.org forum about the sort of clock speeds that you can overclock the 6502s to reach, and a guy called Plasma over there did some really good experiments maybe 6 to 8 months ago now, and I think he was achieving clock speeds of nearly 40 megahertz, which is really nice. So I designed up this computer and built out a breadboard prototype which worked really well, and then I went ahead and made a PCB version of it, which you can see here, and this runs even faster than the breadboard prototype does. It's basically the same design, but just on PCBs instead. So I'm not going to talk too much about the architecture of this computer. I'll put some links in the video description to the forum thread where I was discussing this with all the smart people over at 6502.org, and I'll put a link to a Hackaday page I've made for it as well, which is kind of a high-level summary of the design with more photos and schematics and things like that. But the basic idea of this system is that the CPU and the RAM run at a very fast clock speed. This one here is running at 25.175 megahertz. On the PCB prototype, that's actually running at 34 megahertz at the moment. And that clock is only used for the CPU and the RAM. All of the rest of the board, including any I/O and the ROM, is actually run at a slower clock rate, which comes from this oscillator over here. And this one over here is 4 megahertz. So anytime the CPU needs to access ROM or do any I/O accesses, for example to light up some of these LEDs or to talk to a 6522 VIA, the CPU's clock speed gets slowed down to match this oscillator, then it does that transaction, and then it goes back to running fast again from RAM. And the idea is that your code should live in RAM, everything your computer is normally doing should happen in RAM, and it's just a few exceptional things that have to go through the slow path. And by isolating those things off, what we can do is get the computer to run at a very fast clock speed almost all of the time. Now this is called clock stretching, and it's not a novel idea by any means, but I really went to town on it here. I was very strict about only having the CPU and the RAM on the fast side of things. I didn't want ROM slowing it down, I didn't want too many things being on that bus slowing it down, and that does seem to have paid off in terms of being able to achieve quite fast speeds. As I said, I don't want to talk about that too much on this video. If you are interested though, do let me know in the comments and maybe I'll make another video more specifically about this computer design. But this is the computer we're going to be connecting the serial board to, and it should be easier than it would have been with the one I had derived from the Benita computer, because this one has much better I/O decoding. We actually already have a 74138 decoder in here, which can be used to control up to 8 different devices. One of the devices is this little panel of LEDs up here, but the rest of the slots are all open there, and we can use them to allow us to communicate with the serial device. When we hook the serial device up to this circuit, it is going to be connected to the I/O side, not the CPU and RAM side, obviously. So the relevant clock for the serial module is going to be this 4 MHz oscillator, not the 25 MHz one. So when we're doing things like calculating our baud rate, it'll be based on this 4 MHz clock. That's the one that's going to be feeding the serial board. So let's start hooking this up. I'm going to pop it down here for now. Actually, I'll move it over to this side of it. And we need to connect the data bus up. Now the data bus is actually buffered from the CPU, so the I/O side of the circuit is meant to be on the top side of this bus transceiver, not the bottom side. And like I said before, I don't want lots of things loading down the side of the circuit that's meant to be running really fast. These devices are slow devices, they can go on the slow side of that bus. And for no particularly good reason, I put the signals in a bit of a funny order here. Oh, I've also got this ground wire I should connect through as well. Let's do that. We're going to need a power wire. I'll just run that up there for now. It's a bit messy, but never mind. Now the clock signal is coming from this red wire, but that's not going to be long enough, so let's change it for a much longer one, because it needs to reach all the way up to this oscillator up here. I'll just connect that on there, make a nice big aerial. Now when we write data to a particular I/O port, we want to latch it into this register down here and have the shift register start shifting it out. And that's all driven by the orange line here. So I need to connect that to the address decoder, and I'm going to connect that over here, which I believe should be the 7th of the 8, which should be the 7th of the 8 outputs that this decoder has. The 8th output is already going to the debug LED port up there. And we also have the status register that we can read back from. As I said, reading from the status register is going to tell the CPU whether the circuit has finished sending the byte it was sending. So that one, I'm going to connect it to the next one down. And I'll explain what they mean when we write the code in a moment. So before writing any actual code, I'm just going to turn it on quickly and make sure that the program I've got in the ROM at the moment, which just blinks some patterns on the LEDs while it does a RAM test, I'm going to make sure that that still works, because nothing we've done should have stopped that working. And that looks pretty good over there at the moment. It's sort of flashing up through the addresses as it tests them, and there's a kind of progress indicator at the bottom there. So that is what it's meant to look like, so that's good. We can write some code. So here's a basic shell of a program for my new computer. I'm writing most things based on this sort of starting point. You can see I've already got a define here for the debug port's address being FF70, so it's probably worth talking a little bit about what the memory map is for this computer, just so you understand what's going on. This computer has 64K of RAM, and it goes all the way from address 0, let's just write that in, let's say RAM from 0000 all the way up to FF no, FDFF. All of that is RAM, and it's nearly 64K. Then there's a piece of ROM from FE00 up to FEFF, which is only 256 bytes. Then there's I/O going from FF00 to FFBF, and then there's more ROM at the very top of the memory map going from FFC0 to FFFF. So this system is very RAM heavy, and that's because the computer is optimized to run as efficiently as possible from RAM. The idea is you probably don't want to be having a lot of code in ROM. In terms of how we get the code into RAM, that's another matter that I'll have to deal with another time. But for now, since we are writing this code in ROM, it has to fit within quite a small footprint here. So it's going to start at FE00, and that's why this file actually fills the ROM with zeros all the way up to FE00 at the start, because although the ROM chip is quite large, the computer can't actually access that. This debug port at FF70 is within the I/O range here, and the way that works, if you remember, I said that the 138 decoder on the circuit board had 8 outputs, and the different I/O devices are basically given 16 bytes each. And the first I/O device, device 0, is at FF00 to FF0F. And then I/O1 is at FF10 to FF1F, and so on. You can imagine what the rest is like. So the debug port is on FF70. Any address in the FF70 to FF7F range will actually hit the debug port. It's listening to all of them. Now, if you remember, I connected the serial output port to the one before the debug port, so we're going to have a serial data. Actually, I'm going to call it serial TX data. That's at FF60. So when we want to transmit data, we can write it to any address in the FF60 to FF6F range. And in terms of checking whether the serial system is busy, whether we need to wait before we send the data, there's also the status register, which I'll call SCR stat, and that is on the previous I/O line from the transmit data port, so that'll be FF50. This is obviously not very efficient because these are single devices taking up 16 addresses in memory. For a final solution, what you would do is you would have all of the serial related I/O ports within the same range here, and then you'd have further decoding inside the serial device to work out which one of them is being addressed. But I haven't set that up, so we're doing it this way for now. So given those port definitions, the code enters here. All this is doing is setting up the CPU in a known state. All of the registers and everything gets set to a specific value at that point. And then the code is just doing an infinite loop here. So before that loop, what we want to do is send some data. Now normally when we send a character to the serial output, we're going to want to check the serial stat port first and make sure it's okay to send. But right at the start, I'm not entirely sure what state that flip-flop is going to be in. So probably the best thing to do at the very start of the program is to just send any old byte down the serial port. I'm going to send a 0 with STZ just because that's easy to do. And all I need to do is store it on SERTX data. And now we can't send anything else until sirstat says it's okay to do so. So we probably want to wait for sirstat now. So I'm going to make a little loop here called serial wait. And all we're going to do is bit from sirstat, the status register for the serial system. The bit instruction will read a byte from that address, and it will set some flags based on the value it read. And in particular, if the top bit is set, it will set the negative flag, and if the top bit is clear, it will clear the negative flag. And because the top bit of this register is the one which says whether it's okay to transmit or not, that means that we don't need to do any specific comparisons here. We can just simply use bit, and then if that top bit is not set, if the result is positive, we want to branch back to serial wait and basically carry on waiting. So it's not terribly important for a busy loop like this to be efficient, let's say, but if you can, it's useful to put flags like this on the top 2 bits of the register, because that does allow the bit instruction to immediately test those for you without you having to involve any CPU registers in the mix. So once that serial wait is complete, we might consider sending some data. So let's load the A register with the ASCII code for, let's say, the letter A, and all we need to do is store that to sir.tx data. It's the same thing we did up here, but instead of storing a 0, we're going to store the letter A. And let's not leave it at that. We should probably wait again now and then send a different character. So in order to make it easier to wait, let's move the serial wait thing over here and make it actually something we can JSR to. Then we can reuse it. And let's send a Z next. And then we're going to enter this stop loop, so that's fine. So what this is going to do, when the program starts, it's going to send a 0 down the serial line first. Actually, that's a bit pointless. Let's not bother sending the 0 anymore. Let's get rid of that. Get rid of the first wait as well in that case. So the first thing the program's going to do is send an A down the serial line, and then it's going to wait for that to get fully transmitted, and then it's going to send a Z, and then it's going to just go into this infinite loop. So it's a very simple test program to start with. Before I actually burn this to an EPROM, what I'm going to do is just make my life a little bit easier by also storing these values to the debug LEDs. Because that means that if the serial side of things doesn't work properly, I'll still be able to see what the program was doing at the time it failed. In fact, it's going to blast through this so quickly. Actually, no, that is an interesting thing to do, because if the serial wait function never returns, for example, then I'll see an A on the debug port, and I'll know that that's what happened. Whereas if we get a Z on the debug port, then we will know that at least the first serial wait did return, and we tried to send a Z down the serial device. The main tool for debugging this is going to be the oscilloscope, so if I don't see any serial output from this, I'll be plugging in the oscilloscope and having a look at the waveforms that come out of it. But yeah, we can write that, and I just need to make it actually use it. I called that one serial 1. I need to add it to the ROM names. I can hit make, and there were no errors from the assembler. So let's now burn that to the EPROM as well. All looks good, and we'll stick it in and see what happens. There is one more thing before we do that. We need to configure the baud rate correctly, because last time I had it configured based on a different clock speed. So this is the spreadsheet I made last time for calculating the clock divider for different baud rates, and we want 115,200 baud here, and this was previously set up for a 4.5 megahertz clock frequency, giving a divisor of 39. And this is actually the number I got a little bit wrong, because when I programmed this into the counter, I put it on as 39, and the counter actually interprets that as counting 40 times. That's because the counter counts from 39 down to and including 0. So because it counted 40 times, this actual baud rate ended up being more like 112,500 rather than 115,385 as it should have been here. So that's an easy thing to fix in the circuit, but this clock frequency is just wrong anyway at the moment, so we're going to change that to 4 megahertz because that's the frequency of the I/O clock in this system. And you can see over here that the calculated divisor is now 35, and of course that means that the number we need to program on the 40103 down counter is going to be 34, so that it counts from 34 down all the way through 0, counting over 35 numbers and hence dividing the clock by 35. So the lines that control the baud rate are these 8 green wires here. These define the divisor. So as we saw just now, we need to have the divisor be 35, but because this chip counts from this value down to and including 0, we actually want to set this value to 34 in order to get a division period of 35. So 34 is going to be no 128s, no 64s, 132, no 16s, those are all correct. But down here we're going to have to make some changes, I think. So we currently have no 8s, 1 4, 1 2 and 1 1, and we actually need to have no 1s and no 4s. So there we have 32 plus 2, and that's 34. So now we can see what happens when we turn this on. Now we're expecting to see the debug display here show the ASCII code for A first, and then the ASCII code for Z. Now if all goes well, it should actually do that quite quickly, because we didn't have much of a delay in there. We only waited for the serial circuit to send 1 byte, and that is going to be really quick. So in fact what we would probably expect to see is just the ASCII code for Z. So let's give that a go. The first 2 LEDs are not connected, so the remaining 8 LEDs represent the 8 bits of the byte that we wrote to the debug port. So that's 0101 1010. So 010 is capital letters, and then 11010 is the index of the letter in the alphabet. So that's going to be 16 plus 10, which is 26, so that's a Z. Now obviously the point was not to display the numbers on here, but to send serial output through this circuit, and obviously we needed to connect it to a PC or something else in order to see the result of that. So last time I connected it to a VGA terminal from Debugging Innovations. This time I'm going to connect it straight to a PC instead, so I'll show you how to do that. Now the easiest way to connect this kind of circuit to a PC for serial output is using one of these FTDI adapters, which just plugs into the USB port and it provides a virtual communications port for the PC. It's all based on 3 volt or 5 volt logic. I think it's 5 volt tolerant, so we should be fine with that. And what I've got here is just a few wires connected to it. We're not going to need that one because that would have been for the circuit to receive data from the PC. We're only doing transmitting at the moment. So we have these 2 wires. The purple one is connected to ground, and the white one is connected to the FTDI module's receive pin, and we need to connect that to our transmit line. So let's take a closer look at the serial circuit again. Now what I've done down here is I have wired the transmit line from the shift register over here. This green wire, it comes over here, does a little loop up there, and I've brought it in here. So the reason I've done that is because I want to terminate it through a couple of resistors to ground, and I'm going to take the output to the PC from here. The reason I'm doing this, I don't know if it's the right thing to do or not, but the reason I'm doing this is because I have had some odd behaviors from having a PC connected to a circuit which is also being powered from the mains through a USB kind of power adapter. Obviously there is a ground loop here through the power adapter and through the PC, and in some cases the FTDI device ends up actually supplying power to my circuit and keeping some of it powered when I don't want it to be. So I stick these resistors in to kind of discourage it from doing that. I don't know whether it's a good idea or not, but it works for me. So what I'm going to do is I'm going to connect the ground to the ground over here. This breadboard's had seen better days, it's not making good contact there. I'm going to connect it over here instead to the ground on this IC, and then the FTDI device's receive pin connects between these 2 resistors, and I think I've got a 4K7, oh no, that's a 47 ohm resistor there, isn't it? And this one down here is 1K5. So there's a very small resistor between this line going to the FTDI device and my transmit line, and I have quite a large kind of resistor going to ground here. And you can see actually that the blue light on here has come on, and I don't think that's a good sign. I think that means it thinks I'm actually sending data, so it is still kind of seeing some weirdness coming through there. Anyway, I'm going to turn the circuit on now and see what happens. And again, the LEDs are displaying the ASCII code for Z. The blue light's gone off, so at least we're not sending data all the time. I guess that's a good sign. But what we really need to do is actually activate a serial terminal on the PC, do it again and see what comes up. So let's do that again with a serial terminal overlaid. Okay, so here's the serial terminal. Let's turn it on and see what happens. And that looks good. And I can reset and make it run the program again. We should get another AZ every time we reset it. So that's nice. Working as expected. So I think one final test I want to do with this before moving on is to make it continually output something and then just check that there's no issues with the kind of rate limiting. Make sure that the status register is correctly telling it when the data gets through and things like that. So I'll set up that change in the code, and then I'll set up the oscilloscope so that we can actually look at the trace that's coming out of it and make sure that we're getting a nice continuous stream of characters from that. So I set this up to capture 3 signals. The bottom signal is the serial signal, which looks pretty good to me there. The blue signal here in the middle is the transmit signal. So when the CPU wants to transmit, this little blip down here is the pulse that it's sending on that signal to start sending a byte. And the red signal up here is the finished transmitting signal. So remember, that's the one that I added to the circuit since the last video, which counts the bits, and after 9 bits this goes high, and it goes low again when it starts sending a new byte. So you can clearly see what's going on here. The CPU says send, the start bit begins, which is a low bit always, and the transmit data register empty signal is ended at that point, meaning that the transmit data register is not empty anymore. We have a 0 for the start bit, then we have 0 is the lowest, the least significant data bit, then a 1, then a 0, then a 1, blah blah blah, and over here is the stop bit. This last one here is the stop bit, and after the stop bit the transmit data register empty signal goes high again, and the CPU notices that, and here it is sending the next byte. So we've actually ended up with 2 stop bits here. There was a little delay from that signal going high to the CPU actually sending the byte, but that's okay. Maybe we're losing 1 bit of speed that we could get back sometime, but it's not a big deal. And if you read the bits from right to left, ignoring the stop bit, you get 0, 1, 0, 1, 1, 0, 1, 0, which is again the ASCII code for Z backwards. In terms of the frequency, ignore that thing at the bottom, it's never very accurate, but we're using 20 microseconds per division, so the gap between the large grid cells here is 20 microseconds, and I'm not sure whether we can easily see. Maybe if I zoom in a bit more we can measure one of these pulses, but you should find that each pulse is about 10 microseconds. So now I've zoomed in a bit, the time base is 10 microseconds and the pulses are about that long. So that's what we'd expect for 115,000 Baud. If it was 100,000 Baud, that'd be exactly 10 microseconds. So that's looking pretty good. Now it's also possible to ask the oscilloscope to actually interpret that signal and display what it means, and that can be quite handy, but I can never remember how to do it. If you have an oscilloscope that can do that, it might be worth figuring that one out because it can help with debugging stuff. So there we have it, serial transmit boards working well. I guess the next thing to do is to implement a serial receive circuit, so let me know if you're interested in that and I'll see if I can make a video covering that as well. Because once we've got a serial transmit and a serial receive, we'll have basically a full 2-way communication layer there, and then we can start doing things like transferring code across from PCs or whatever. So yeah, that's quite cool. Do let me know in the comments what you thought as always, and hopefully I'll see you next time.